So we've been looking at, I've been looking at, we've been doing, I've been doing, maybe you've been watching, I don't know, maybe you did it yourself. Linear drag versus quadratic drag. And so today I want to look at this classic physics demo. And the demo says, if you take two objects and you drop one at the same time you shoot one horizontally, and they on level ground, which one's going to hit the ground first? And the answer is usually they both at the same time, not always. Okay. So let me go ahead and show this demo to you. I'm going to show you two versions of the demo. I'm going to show you a video. One is one that you can do at home, and one is from the MythBusters, which is really well done. Let me show you the one from that you can do at home. Okay, so this is a demo. This is on my other YouTube channel, and I'll link to this down below. So the idea is I have a coin right here on the edge of the table, and then I launch another coin and it hits it. And so when that happens, the launch coin will keep on going and this one will drop down. And it's a pretty easy demo to do. This is in slow motion. So there's the other coin, and it's going to flick it. And so this has a glancing blow. And you can see they hit at the same time, and then the dog's like, wait, we're dropping money? Okay, so that was that. Here is the MythBusters. I'm not going to show you the whole thing. Let me explain what's going on. So they wanted to show this with a firearm by shooting a bullet and dropping a bullet, because that's what usually it says in textbooks. And their original try was to just shoot and drop at the same time, but then they couldn't make a comparison of when they hit because the bullet hit all the way down the range. So what they did was they rigged up a system that dropped a bullet way far down where the other bullet would hit. And they used a slow caliber, like a 45. I don't know anything about guns, but they use a slow caliber bullet to do this. Let's see. So let's just skip forward to there's they shoot it there, and they don't hit the same time, but they're pretty close. Okay, it's a pretty difficult experiment to set up. You got to make sure the gun's level. You got to make sure that the drop bullet is dropped at the same time as the launch bullet. You got to have them landing at the same place so that you can see them. And I think overall they did a pretty good job. Not as good as that one physics demo with the truck driving 50 miles an hour, shooting a ball backwards 50 miles an hour. That one, that was good. Okay. And yes, I didn't work on this episode of MythBusters, but for the last 5 years, I was the science consultant, the technical advisor for MythBusters, just in case you know. So I do know something. And you can look it up. You don't believe me. Look it up. Okay, so let's go back over to the paper here. And let's talk about why this demo works. So first of all, we're going to do this with normal projectile motion. In normal projectile motion, there is no air resistance. And then we have linear projectile, linear motion, linear drag. And so in that case, the drag force is proportional to the velocity. And we use the drag coefficient B. And then we have quadratic drag, which is proportional to the velocity squared. Oh, this is V hat. I'm sorry, I wrote that wrong. So negative some drag coefficient, the velocity magnitude squared, and you have to multiply by a unit vector. It is very possible that you could have a combination of these two. I'm just going to do linear drag and quadratic drag separately just to make it simple. Let's start with this no air resistance case. So if I only have that force, I can write this, F net equals m dv dt. And let's actually say this is v1. It's object 1 is going to be, this is 1 and this is 2. So I'm going to drop 1. Okay. So in that case, I can just deal with the y direction, and this is going to be equal to mg, the vector. But in the y direction, this is going to be m dv1y dt equals negative mg, right? Because now I'm looking at the y component of the gravitational forces in the negative direction. That's fine. And so then if I divide by m, I get, and multiply by dt, that's what I would normally do, I get dv1y equals negative g dt. And that's a differential equation that we can easily solve, but the most important thing here is y10 is equal to some constant h, vy10 equals 0. So I'm dropping it, it has 0 y velocity, and it starts at some position h. I need those two initial conditions to integrate this twice to find position. I'm not going to do that. Okay, I already did that. I'm not going to do it again. Now let's look at ball 2. Ball 2 has the same equation. F net equals m dv2 dt. But now I really have two equations, right? Because it does have motion in the y direction. I mean, in the x direction. So I actually get a y equation, m dv2y dt equals negative mg, and then I get m dv2x dt equals 0. There's no forces. So in this case, I could integrate, and I don't really care about that. What I care about is this. This equation becomes the following. If I can do the same thing, and I get dv2y equals negative g dt, and it's the same differential equation, and since it's launched horizontally, it has the same initial condition in the y position and the same initial condition in the y velocity. So it has the same differential equation, it has the same initial conditions. So that means the motion has to be the same. Has to be. Same. Okay, so that's why they hit the ground at the same time. And I'm going to make a VPython model of this, of all three of these, but just hold on. Now let's look at this case, linear drag. Okay, so now let's do the same thing. Here's ball 1, here's ball 2. That one has some initial velocity in the x direction. This falls down and hits the ground. Oh, that one goes like this. Okay, and they hit the ground at the same time. So let's do the same thing. For this one, I'll say F, let's call this 1 and that 2. F net equals m dv1 dt, and that's going to be equal to negative mg, no, plus, because it's a vector, minus bv. Can I break this in the x and y direction? Yes, I can. So let's write this as just the y direction. I get m dv1y dt equals negative mg. So now, let's say it's moving this way, but it doesn't really matter. If the y velocity is negative, then the air resistance would be up. So I can write this as negative bv1y. You can do a bunch of tricks here, but let's just divide by the mass, and then I'll leave it like that. d1y 1y dt is negative g minus b over m v1y. Now, I did solve this equation. I solved this differential equation in a previous video. The link to my whole playlist of videos will be down below. But if you can't find it, just send me a comment down below, and I will give it to you. Okay. So there's my differential equation. I'll leave it like that. You have to get it variable separable, and to do that, you need a little trick. But I can say y10 equals h, vy10 equals 0, because it's released from rest. Okay, now let's do 2. F net equals dv2 dt, this is a vector equation, equals mg minus b v2. That's a v1 up there. So it's the same up here, okay? But the difference is that, okay, let's just go ahead and break this into a y equation. So because I'm dealing with the velocity vector here, I can get the y component. It's just the y component of that v1y. So in fact, I get the same thing, right? I get the y component for this, I get the y component for gravity, I get the y component of that, and I actually get the same equation. Let me write it down here. dv2y dt equals negative g minus b over m v2y. Now let's do the x equation too. So here I have dv2x dt, oh, there's an m there, sorry, equals m. It's going to be, there's no gravitational force in the x direction, so I just get negative b, and then I get the x component of the velocity, so it's just going to be v2x. And that's another differential equation. But this one is one I care about, because this equation only depends on y20 equals h, v2y equals 0. It only depends on the y velocity, which is the derivative of y, and y. There's no x's in here. So in terms of these two equations, they're identical. Well, one has a 2 and one has a 1. So if I drop this y motion is going to be identical to this y motion. Okay, and I'm going to show you that. So they hit the ground at the same time. Okay, one more case. Now let's do it again. But with quadratic drag. So I'm going to first do mass 1. Mass 1, I get, this is just dropped. So I get F net is mg, the mass. Okay, but then I have to, oh, and that's going to be, I'll write that at the end. And then I have the drag force. This is going to be minus c times the velocity vector v squared times v hat. Okay, now I technically could write that. So this is something that we need, and that's going to be equal to, this is 1, 1. So it's going to be m dv1 dt. That's the acceleration. Let's just rewrite this because it's a little awkward to deal with it this way. Because remember, what is the unit vector and what's the magnitude? So I can find the magnitude of a vector. I think that's okay. I could say v1 magnitude is going to be the square root of v1x squared plus v1y squared plus v1z squared, if it is 3 components. What about the unit vector v1 hat? This is going to be the vector v1 divided by the magnitude of v1. Okay, so, but if I square this and I multiply by this, then I get v1 magnitude squared v1 hat is the same thing. The v1, one of these magnitude is going to cancel, so I can write this as the magnitude of v1 times v1. That's the same thing. And it's just going to make things a little bit easier, not that it really matters. We don't have to deal with unit vectors in. Okay, so let's write down the y equation for mass 1. There's only a y equation. Okay, so I'm going to write that as m dv1y dt is negative mg, because that's the y component of that. Now, if it's falling, I do have to be more careful about the sign here, right? Because that's going to be positive. And if this is moving down, that's negative. So I want the force to be up. So this actually does work. Negative c times the magnitude of v1 times the y component of that is going to be v1y. And the minus sign is okay. But you can see that we have a problem here. This is the magnitude of v1. And the magnitude of v1 depends on v1x and v1y. So let's write this out as negative mg minus c times the square root of v1x squared plus v1y squared. I'm going to say there's no z component because I'm lazy, times v1x. And that's going to be equal to m dv1y dt. Now, in this case, v1x is 0, so that's gone, right? Because I drop it. So I get m dv1y dt equals negative mg minus c. Now here, I just have the square root of v1, y. This is y. That's a y. The square root of v1y is v1y. So I just get essentially v1y squared, and this will work as long as it's falling. This only works for falling, right? Because if I have that going up, then the drag force would be down, but I'm squaring that velocity, so it wouldn't work. Okay, now let's look at mass 2. For mass 2, I have the same equation up here. But if I look at the y equation for mass 2, I get this. M dv2y dt is negative mg minus c v2 magnitude v2y. And now I do have an x component. So if I put this in, I get the following. M dv2y dt equals negative mg minus c square root v1 v2x squared plus v2y squared times v2y. And that is not the same differential equation. And it's not an easy one to solve. This is a really difficult equation to solve because it doesn't just depend on y. There's an x component in here too. This is the time derivative of the x position. So it's a tough equation. But the answer is that these two do not have the same vertical motion. They do not hit the same ground at the same time. Which one will hit the ground first? Well, this one's going to have a smaller drag force because this is v1 y squared. This is y squared plus x squared square rooted, so it's going to be greater. So it's going to have a greater drag force. So this one's going to, the drop ball, 1, should hit the ground before the shot ball. Okay. Now for fun, let's go ahead and model this. I'm going to model 6 different balls in Python. So I got a little head start just because I didn't want to waste too much time, but apparently I'm wasting a lot of time. So let's switch over here to Python. So now I'll give you the code for this. So this is GlowScript v Python. What I've done is I made a ground and I made the ball. So the first thing I'm going to do is I'm going to take a ball and just drop it, and then I'm going to take a ball and shoot it sideways with no air resistance. Then I'll do linear, and then I'll do quadratic, and we can see. I didn't tell you, but I am going to model this using the numerical calculation of calculating the force during a short time interval and using that to find the change in velocity. I didn't describe that, so I apologize. But we'll, if you have, I've done this in previous videos too, so you can go back and look at those. Okay, so let's just run this. See if, oh, that's not that. Run it down here. Okay, so there's my ball and there's my ground. That's cool. Okay, so but I need to model the motion. So I have the ball. I gave it a position. I gave it a radius. I'm going to leave a trail with points and all that stuff. I gave it a mass. I gave it an initial velocity of 0. I need all that stuff. Now I need a time, t equals 0, a time step. I'm going to put a small time step, 0, 0, 1, because in air resistance, when I start squaring those velocities, it might make a big difference. And I want to run this until the ball gets to y is equal to 0. So I'm going to say while b1.pos.y is greater than or equal to 0, then do the following. Rate 1000, which I'm going to change. Step 1 is to calculate the force. I'm going to call this force F1. F1 equals b1.m times g. That's it. There's no drag forces, and that is a vector equation. G is a vector up here. You see that G? So this mass is scalar. I get a vector. Now I can use that to update the velocity. b1.v equals b1.v plus f1 times dt divided by b1.m. So f1 divided by b1.m is the acceleration. I multiply that by dt, and that tells me the change in velocity, so I can change the velocity. I'm going to put a space here, and let's put a space here. Okay, now I need to update the position. b1.pos equals b1.pos plus b1.v times dt. That's it. Update time, you don't really need to do that. Time equals time plus dt. And let's run this. It should just be a falling ball. And it might not, because I make mistakes. Okay, but I like these dots it leaves. You can see that it's going faster just by looking at the dots. That's kind of cool. Okay, let's make another ball. So I'm going to just copy all this. And there are better ways to do this. You can say that's not the efficient way, but I don't really care. I'm just going to change this to 2. I'm going to change this position to, I want to move it over a little bit so it's not on top of each other, to b1.pos plus the vector twice the radius. So it's going to be 0.100. I think that's right. Same radius, same make trails, same points, same mass. The velocity, I've already listed up here, v0 is 4. So I'm going to put this as v0. So that's B, that's that. Now down here, I need to calculate, I could choose the same force, but I'm not going to. F2 equals B2.m times G. I could copy this. Change these to 2, 2, 2, 2, 2. You gotta say it. If you're all by yourself and you're not saying that, it's not going to work. Copy this. Change it to 2. I should have, maybe I should have made all this code beforehand, but I kind of like doing it live. Okay, let's run this. That's pretty cool. This is in 3 dimensions too, just so you know. But you can see right here, they hit the ground at the same time. Let me run it again because it's a little tilted. And not only that, these dots line up, right? So the Y position at every one of these dots is the same. So it's a pretty good demo right there. I just like that. I'm fine. I'm happy with that. Okay, now let's make, I'm going to say B equals 0.1, C equals, what did I use for C? Which 0.1. Let's do that too. So B is the linear drag coefficient, C is the quadratic. I'm going to put them at the same. We can change them if you want. So I need to make another mass. Call it B3. And just change these to 3. I'm going to move it over a little bit more next to B2. I'm going to change the color to yellow. Color equals color.yellow, just so we can tell them apart. And then I need to change this to B3. B3. This one's going to be dropped, but with linear drag. Now down here, I need to do F3 equals B3.m times G minus B times B3.V. That's my linear drag. This equation is the same though, right? Once I calculate that force, it doesn't really, the update velocity is the same. I just need to change these to 3, 3, 3, 3. I told you got to say it. If you don't say it, it don't work. Copy this. And change them to 3, 3, 3. Okay. Now let's run this. So this should have an extra, the third ball. And right away you'll notice that it doesn't hit the ground at the same time because there's an upward pushing drag force. That's kind of cool. And it's yellow. That's kind of cool. So now I'm going to copy this. And let's make 4. It's the same thing. Just change all these to 4s. I do want to move it over again, so it's going to be B3. Other than that, I just need to change this to 4. Change this to 4. And then give it an initial velocity of V0. Then down here, I'm going to copy this one and change these to 4, 4, change this. I don't know, maybe this is boring, but the end is good. It's going to be good. And maybe, you know, we could talk about stuff while we're typing too, right? You know, I think we could talk about the fact that I think that, you know, there are better ways to do this. You could put all these balls in a list, and it'd be a list of balls, and that'd be pretty cool. But there's only 6 of them. I mean, don't be bullied into trying to make things more complicated than they have to be. And nothing has. See, I made an error. F4. Wow. I didn't say it out loud, did I? Okay, but that's pretty good, right? You'll notice that both the yellow balls don't hit at the same time, but they have the same height. That's the same height. I mean, if you want to print them out, we could. I'm not going to do that because I want to show you quadratic drag. So we need to make 2 more balls. Should I make them both at the same time? Yes, let's do that. So here's 5. And these are going to be plus 4. And then I want to make these cyan. My favorite colors in Python are yellow and cyan. They just show up well against the black background. If you use like red and blue and green, they're just not as bright. And I don't like that. So this is going to be 5. 5. And 5 is dropped, so that's 0. And then let's do it again. Let's make another one. 6. And this is going to be 5. And this is going to be 6, 6. Okay, so now down here I need to do F5. So let's go over here, start from the right. F5, 5, and this is going to be C. Did I use capital C? Yeah, I did. C times B5 times the magnitude of B5 dot V, right? So that's one way to get that V squared with the unit vector. You could do magnitude of V squared and then multiply a unit vector. It gives you the same thing. And now let's do that again for 6. Just change these to 6s. 6. 6. Okay, so down here for the velocity, I'm going to copy this. I'm going to paste it twice. Why is that not scrolling down? Okay, now I'll change this one to 5. Change this one to 5. 5. Oh, change this to 5. Oh, it doesn't really matter. The maths are all the same. 6. 6. 6. 6. See how fast I am? Okay, and then we're going to go down here and copy this twice. We're almost done. I like to pretend like I'm the Bob Ross of Python, but you know, you make your own judgments. If you've made it this far, then that's probably not a bad thing for me to say. Okay. 6 balls. Let's see if it runs. And it didn't. Can't find F6. Same mistake I made before. Right here. Why didn't I change that one? That's weird. Okay. Oh, I didn't give it a velocity. Okay, this is V0. Okay. Boom. That did it. Okay. The balls with no air drag both at the same time. The balls with linear drag end up at the same vertical position, but that's not true for the cyan balls. It's obvious that these are not the same position. They're not the same height. Okay, so they do not hit the ground at the same time. If you do the coin trick and you have to include linear drag, they will work. Where you shoot them off at the same time. If you do the trick and it's quadratic drag, no worky. Okay, so I'm gonna save this code. I didn't give it a name. That's weird. Let's say no drag versus linear versus quadratic. And you will have the code down below. I will also give you a link to my classical mechanics playlist that I'm building, and so you can see all the other videos on air drag and stuff like that. So that's that.